He is occasionally, but happy, he his us. Easy attention. So our speaker is a professor at the Department of Statistics. So they're really like Edwardsville. This research interests are survival analysis, reliability evaluation, completion stage mathematics, translation probability, and other states are only state leaders. The receiving steps of mathematics, New Jersey Institute of Technology, NSCS combined with specialization research from the University of Science. At the moment, it serves as the department's graduate program at the university level. He has served as graduate chair and is currently served as faculty senate president. Ang kakabas ko sa akin ay school of chair, faculty senate. And first of all, what Marcus and senior and he's also the law. That's a thing. So without further ado, for big much time for lecture, so let's take a look at Professor Marcus.
Thank you, Net. First, I'd like to thank the department, mathematics here at Ateneo, for taking time in inviting me, and so I could share some of my work with my colleague, Dr. Zenia Agustin. We also call her my Agustin. Sorry, it's the states it's Agustin. Okay, we have to say Agustin, doing the like different spelling of our last names. Students at SIU call. Tell them, Colin, she's my better half. And she always says that she's the better half, but I always tell them I was the first Dr. Agustin or Dr. Agustin because in our commencement, I was the first one who got hooded. So it was a great joke. As what Dr. De Peñas mentioned, so my areas in reliability and survival analysis. So I'm gonna just share with you some of my joint work with Xenia and some of the results here, also with some of our grad students, some continuing, some have already graduated. So I think it's this one. So which button should I? Take long to adjust stuff. Okay. So let me kind of just give you an introduction. So imagine you have a system, in particular a series system. So a series system, you think of like say components in series. So when you have a component system in series, the failure of the system is due to the failure of one of the components. So when a component has failed, obviously you are not going to see the failure of the other one. So in some sense, there's some sort of like censoring going on. So imagine, so you have m components. They could be different individuals. They could be individuals. They could be, let's say, for instance, some social groups. Although the main motivation or the main language I'm going to be using is on reliability, in particular software reliability, but the results could be applied in that area. So each component, their lifetimes are independent. So there's going to be some probabilistic model for detailing their lifetime. So the failure, as I mentioned, the failure of a system is due to the failure of a single component. So the whole idea is when a component, so just imagine you have two components, right? If this is the component that failed, the idea is you want to improve this component. You're not going to touch the other one though. So it's just this one. And so what you have is we're going to make an assumption that there's one defect or bug that caused that failure. But when you are a debugger, you're not going to be perfect. Okay? Unless, as what I tell my students, to tell my wife, unless the debugger is my wife, that's the only time you have a perfect debugging. So if me, I probably would have this probability P. Okay, so this probability P is a number between 0 and 1. 1, we accept 1. We probably don't want 0 because that's like, well, why do you have a debugger that basically cannot improve? So anyway, but the interest is not just simply improving the component, it's still more what is the reliability of the whole system. I'll define what the reliability is in second. So let me just give you some background literature. In 72, this is probably, I believe this is one of the earliest software reliability models is a model by Jurinski and Miranda. And the whole idea here is, so here, this is what we call as a hazard function. Just think of it as kind of like a rate to failure or something that gives you the rate to failure. Notice it depends really on two quantities. Those two quantities, this quantity alpha, which is some sort of a failure rate contribution of a bug, and capital B is the number of bugs or defects at the beginning. In Jurinski and Miranda, their whole idea was just to find what we call as estimators of alpha and B, because those are what we call as unknown parameters. They're constant, but then you don't know them. That's why you have to estimate. Probably one of the most quoted papers in software reliability, but also one of the ones that where they kind of also say, well, let's change this, let's update this. And so the next one by Bev Littlewood in 1980 kind of, I would say, improved, but then extends the Jurinski-Miranda model, where notice now, like if we go back, how do I go? Yeah, right. Okay, so if you notice, essentially in the Jurinski-Miranda model, every defect has like this constant failure. So which from the perspective of how a component or the lifetime would be looked at, it's not too realistic, but it was a needed assumption because it also was like, it makes it much easier in some sense, right? And so the Littlewood model essentially says, well, bugs that cause the failure earlier in the process are deemed to be more important, which makes sense when we look at a certain, like a car, right? If there's really something wrong, say with the battery, we should see it right away, as compared to when there's probably some defect in the tires, but we won't see that until maybe later on. So the whole idea in the Littlewood model is earlier defects that are noticed or observed are the ones that have more importance. But notice for both the Jurinski-Miranda and the Littlewood model, there's still the notion of perfect debugging, right? I mentioned this P earlier. So there's a notion of perfect debugging. And so what they did was, well, let's extend the perfect debugging into some imperfect debugging. Notice here in the goal model that P, right? If P is equal to 1, you go back to the Jurinski-Miranda model. It's basically saying, well, every bug that we find will be able to remove perfectly. This time, though, in the goal model, they said, well, there might be a probability P wherein you probably will be able to remove it, but then there's a probability 1 minus P that you won't be able to remove. Oba and Cho essentially looked at the Littlewood model, and basically the same thing. The only thing now is in this paper, what they did was, instead of looking at the probability of removing a bug, they look at the probability of adding a bug. Okay, which kind of means like maybe in my case, when I would do my computer programming back in the days, I know a lot of you are probably too young, but you won't remember when you have those punch cards. Okay, if you don't remember those, when we used to do programming, we have to put everything in a punch card. That's each line. And then when you had a mistake, You have like 200 cards. There was a mistake in card number 7. Your program will not run. And sometimes it's just like you added like a colon or something. Anyway, that shows my age, but that was what happened in the 1980s. So, and then Mahapatra and Roy in 2012 basically extended goal, and in that paper they kind of also added like there's basically 3 things. They kind of separated removing a bug perfectly with not removing a bug perfectly, and then also adding a bug. Okay, so that's why you have this P, Q, and R. With this sum, they have to be total to 1. Now, what we did in 2014 was we extended the goal model. All of those models that I mentioned only dealt with a single component. But we were more interested in a system, in particular a series system. So what we did was we extended the goal model. Now you have 2, 3 M components, right? Each one had like this probability of um, imperfect debugging of like the probability P. Okay. And so one thing that we did in all of those earlier models, they did not use the notion of counting process. I'll say a little bit more about counting process in a little bit. But so we use the idea of counting processes. Essentially, we want to know how many failures, like say again, I'm looking at the simple case of 2 components, how many failures of the system was caused by component 1. And then you're counting also how many system failures were caused by component 2. But we also look at this, well, we're not just going to look at the components failure. Let's try to think of a task. Simple example to look at is, let's say a task is to sort a file. So you have a file to be sorted, right? And at the end, you will see whether it's correctly sorted or it wasn't. And when it's not, then that means there was a failure in one of the components in your system. So that's kind of like the whole idea. We have this probability P sub j. Now, basically, each component has that probability of removing the bug. And as what I mentioned, is NJT is the number of system failures observed due to the failure of the software. And the main interest is to still find the system reliability, but we will see, we'll be interested first in finding the estimators to those parameters. But then the main objective is to really look at an estimator of system reliability. And the results that I'm going to mention have something to do with finding what we call as the large sample properties or asymptotic properties of the estimators. And so let me kind of give you an idea of the framework before I would look at discuss the results from the 2 models that we have looked at. We think of this vector theta as your parameter vector. Okay. We have this vector of counting processes, this capital N. So I have k components, right? So you have n1 of t, n2 of t. So nj of t is basically the number of like the number of failures due to that component that you observe up to time t. The hazard function, that lambda, we could look at that as a vector as well. And the resulting thing, the nice thing is that when you take the counting process and you subtract the integral of that hazard function, that this integral is also known as a compensator. So you basically get a martingale. And there's some nice properties for martingale that I'll mention that we'll actually exploit in some sense when we try to present the large sample properties later on. Okay. So what's the whole idea? We have a fixed testing period, right? So think of it as if you have a system of softwares. So you're going to test them up to a time tau. So that tau is fixed. You're going to collect your data up to time tau. So all the failures of the components, which means failures of the system. You also collect the time to failures, actual time to failures. And then you also would have that component, that task completion. So at the end of tau, that the time period, you're going to have your data. What you're going to do is we're going to kind of like summarize that data. And we do that by finding what we call as the likelihood function. Basically, what we're going to do is we're going to look at the log of the likelihood function. And in essence, what we're going to do is we're going to take the partial derivative of this log likelihood function. We actually call it the score process. And this partial derivative of the log likelihood function, you're going to set to 0. That's what you're going to find as your estimates of your parameters. Okay, and I'll show you the equations in a little bit. And then what we're going to do is obtain what we call as a maximum likelihood estimator. Okay, so we're maximizing, essentially we're maximizing the likelihood function. But we all know from the logarithmic function is a monotonic function. So the maximum of the logarithm of right likelihood will also give you the maximum of the likelihood function. Okay, and so the idea here is once you get these parameters, you're going to obtain their large sample properties or asymptotic properties. And we're going to actually use, and I mentioned here the regularity conditions, and it's kind of like some 5 conditions, not important to know what they are, but I'll explain essentially what those are. So when you look at those regularity conditions, we will see later on, I'll present a sketch of the proof, is that you're going to be interested in actually finding a Taylor series. So the partial derivative of the log likelihood function, you're going to get a Taylor series expansion. And essentially, you're going to have certain terms, okay? And what we are going to end up showing is that each of those terms would converge in probability to what we kind of want them in order to be able to show the convergence of probability of the estimators. And the regularity conditions basically allows us that if you satisfy them to be able to examine those convergence in probabilities. And we're going to be using Martingale-Central limit theorem. That's basically just like the central limit theorem, the usual one, but in a Martingale framework. Langlard's inequality and Kurt's lemma, those are basically equivalent to the strong law of large numbers, because that's what we need for the convergence in probabilities. And then the multivariate delta method is because, as what we will see later on, the system reliability is a function of the parameters. So we kind of need that multivariate delta method to be able to find properties. And so one of the first things that we're going to explore is basically looking at convergence of the counting process. And in essence, so what we will see is that when the convergence of the counting process relies on solving this integral equation. Okay, so it turns out that the solution to that integral equation is the quantity where, when properly standardized, your counting process will converge to in probability. And that's something that we actually would need. Okay? So let me talk about two models that we have worked on. So model 1 is really the work that we extended for the Judzinski-Miranda model, that imperfect debugging model for the Judzinski-Miranda model, again, for a system of softwares. So essentially, when we're going to assume, and I'm going to add these two pieces. The P sub J, we already saw that. That's the probability of perfectly removing a bug. But we're going to introduce this R sub J, wherein we are now adding the possibility that, yes, you remove the bug, but you may have also added a bug. Now, the PJ and the RJs are assumed to be constants. Okay, so we're not looking at, and they're known. Maybe from a practical point of view, you say, well, that's how good the assessment of the debugger will be. Okay, so we're not interested in estimating them because those are known quantities. Okay. Now, the survivor function, basically, we're looking at the probability that the failure of of component J is going to be past some time t. And so from the model, you'll be able to find quantity and hazard function defined to be the PDF, or the f sub j is what you call the probability density function divided by the survival function. One thing I failed to mention, but I think it's in we want the p sub j to be bigger than op sub j. In other words, we want the probability of removing the bug to be bigger than the probability of adding one. Because imagine if it's the other way around, then we're not probably going to improve really the component, because it's like we're adding more bugs than we could remove. And then the completion time of the task assumed to be independent, and just for simplicity, we assume this to be this constant hazard function, but some of the conditions too allows us to make a more general form for this lambda naught. So, as what I mentioned earlier, after finite observation period, our interest is really the system lifetime. And this is how we're going to define the reliability. So at the end of the fixed testing period, we have all the data. Right? So we have the data on how many failures we observe, the actual time stuff. What we're interested in is, let me give your system, right, that the task has a completion time denoted by the capital C, random variable C. We want to assess the system reliability to be the probability that a task completion will be observed before a system failure is observed. In other words, we supposedly have improved this laptop, right? It's out. So we're going to assess its reliability by saying, well, if I give this a random task to perform, I will observe the task to be completed before it fails. Okay? And then it turns out, again, when you work out the integral, it turns out to be given by that expression. Now, this is where I want down. Notice here, these are your parameters: beta naught, the gamma J naught, and the BJ naught. So those are our parameters of interest. What we see here is that the reliability, or the system reliability, is a function of those unknown parameters, as well as the counting process, or the NJT, the number of really system failures observed due to the failure of component J. Okay, so we keep that in mind, because that's going to be important when we present the large sample or the asymptotic distribution of the system reliability. Now, what's a nice thing? I mentioned earlier that we're used the Martingale central limit theorem. It turns out we have a nice stochastic integral representation of your score process. So this vector H, the predictable process, essentially a predictable process just means that there's this thing called a filtration. Like the filtration is like all the data, right, that accumulate up to the time. But from a practical point of view, just think of the predictability of the process of this H as in everything we need to know about that process, in some sense also in future, is based on what we observe up to the time. Okay, so there's that predictability of a predictable process. The nice thing here is, because of this stochastic integral representation, U is also a martingale. In particular, what we call a square integrable martingale. And that's where that martingale central limit theorem kind of comes into play. And so, remember earlier I showed that likelihood function. So when you take the likelihood function, or the log likelihood, take the partial derivative, set it to 0, it turns out we're going to be solving this system of equations. So these are really what I have m components. So I really have 2m plus 1 system equations that you're going to solve. And remember, I mentioned earlier that the system reliability depends on So also by the way, the beta hat is you saw from here, the gamma hat and the B hat you saw by looking at those two equations. There's really no closed form um, expression for the gammas and the B's. So what we have to use there is really using a numerical solution to find the MLEs, or the one with the hats are your estimators. And so the estimator of the system library is basically replacing the parameters, the unknown parameters, by their corresponding estimators, the ones with the hats. Now, how are we going to look at the large sample properties? The typical thing in like intro stat, when you look at large sample properties, is to say, let's observe like n observations, then we say, let's take n going to infinity. Well, we didn't really do it in this manner, in the sense that we're not going to say, let's just observe so many failures. Going back to the perfect debugging, if you are going to just say observe so many failures, you have a fixed testing period. At some point, you're supposedly going to remove all the bugs. Now we're going to have the realistic thing that we're not going to be able to remove all the bugs. So this is what we did. I want you to focus this one. So what we have is this alpha j. Okay, this alpha j is, to think of it up this like a unit, like for a unit period. So again, thinking from a software point of view, you might say, well, what is this alpha j? It's like the number of typical of the bugs that we could find in, say, every 100 lines of code. So we think of that alpha j as that unknown parameter. And so the way we're going to look at it is, as n gets to infinity, so this s of n, we think of that as the size of the component, then we multiply that s of n with alpha j to get the number of bugs for the nth model. Okay, so what happens here now is that for inference, the parameters we're not going to have the b, we're going to have the alpha. So this is now going to be your true value vector. And once again, the solving for that integral equation, we're going to end up with this quantity. Now it turns out now, for a first result, is that as n goes to infinity, when the nth model, right, counting process for the jth component is standardized, right, or by dividing by the s of n, that converges in probability to that process x of j. Okay, so that's very similar to what we call in probability as like the strong law of large numbers. In like as n goes to infinity, I think the typical thing that we see in intro stat is like when you have the sum of the x's, I go from 1 to n, divide by n, and then that conversion probability to supposedly the mean, right? So that's kind of like that same analogy here. And notice we will also be able to find a quantity. That's actually important because that's basically, as n is large, that's what we expect will be the residual number of defects in that component. So we're able to have that a factor of that alpha j naught. That's a nice thing because you have that exponential term that's really e raised to a negative, that quantity that's really positive. So it's like saying, well, the residual number of bugs would have to be smaller than the actual number of bugs for that size. So that's good because that means we are improving. Okay, so again, depending on the piece of j and r sub j and the t, that also obviously will kind of tell us how good that debugging will be. And so the interest now is to find the asymptotic distribution of theta hat. Just some quantities. So the script, assuming the second partial derivatives, and then the script R is like the third partial derivative of your log likelihood function. And we were able to show the existence of a consistent estimator of theta, or the theta hat, which is theta hat, and also able to establish the convergence in distribution that Z is really like a standard normal, a multivariate normal random variable. Now, I'm not going to present the proof, but let me just kind of explain, because I mentioned also some of the results that we have used. So essentially, the whole idea, this was actually a method by Borjan in 1948. What you do is you take a Taylor series expansion of your log likelihood function, and what you have to address is to look at these three convergence and probability results. That's where those conditions, the regularity conditions I mentioned earlier, and we were able to show that the log likelihood function that U divided by Sn convergence probability to 0, and then this quantity is just the entry of that matrix, the variance covariance matrix. And then what we're basically saying in the third one is that really the third partial derivative has to be bounded. Okay, so that's why we need to establish those results. And then for the convergence distribution, again, from the Taylor series expansion, looking at each term to show the appropriate convergence in distribution and in probability. Now remember, the interest is the system reliability. The estimators, they're good, but that's not our main thing. And so what we have to do is that's where we have to now use the multivariate delta method, because what we're going to do is we have to first establish the convergence and distribution that vector. So the theta hat plus the counting process. And then once we establish that, we use the multivariate delta method, and then we're able to find the actual large sample properties of your system reliability estimator. So again, some results there. This matrix gamma is the one that we need for the variance covariance matrix of the theta hat and the counting process. Now let me kind of just mention that second model that we have worked on. This is now basically that Littlewood model, but now we have that imperfect debugging probability P sub j. Okay, everything is basically kind of set up in a very similar fashion. Same thing when we assess the system reliability. Same thing at the end of the testing period. You basically would like to give a task. You want to find the probability that the task is completed before the failure of the system. Log likelihood function. And same thing, we were able to also look at the stochastic integral representation of your process. Reliability, same thing, you notice it's still a function of the parameters and the counting process. And same large sample model, right? Obviously a little bit different for that process x sub j, again solving that integral equation. And we were able to again establish the convergence probability of the counting process, the convergence probability of the existence of an MLE, basically existence of a consistent estimator, and then its large sample distribution. And same idea as what we had earlier, right? So multivariate delta method, you're again interested in the distribution of that vector. So it's the MLE, theta hat, and the counting process, partial derivatives, all those partial derivatives here. Then we're able to establish the asymptotic distribution of your system reliability estimate. Okay, so let me kind of finish up some concluding remarks. And so I think I just want to really mention more the completed ongoing future work. Um, Z and I had a student. He completed one of his like in his master's thesis. He looked at the finite sample properties of the estimators. Problem here is we want really actual data, but I found out they attended the conference. I was still I just graduated. I attended the conference. My advisor, was also actually Filipino, introduced me to a professor from University of Maryland. He did some work in reliability, and we were talking. Yeah, we want some data, and they said you're not going to find the data because those software companies will not give you the data. And even if you have the data, you probably cannot publish the data because you have to be working for them. So I don't want to work for them, but that's okay. So what we're doing is we're doing a simulation study for the finite sample properties. There's some data that are out there, but they're more for a single component. So it's hard for us to actually extend it to a system or a series system. So the student that I have, he looked at the finite sample properties for the imperfect debugging. Also consider a stopping time. I have one student in like 2022. He looked at the one for, he established a stopping time procedure for the model one that I presented. And then the same student so less than a year ago, right? He graduated less than a year ago. He looked at a stopping time for the model two. And then, so obviously one of the things I'm working on, I have a new student, an incoming student, talking with Lynette. He was able to get a visa to go to start. So I was happy about it. So he's also going to be looking at some of those finite sample properties. But then for that model two, we're adding that notion of having a probability that you'll add a defect or a bug. But I think the objective really is to have a more general imperfect debugging model, which basically would have those P sub j's to be a function of time. Okay, so what we did then, we had some initial work on that, and I think I've mentioned in some of the papers that we looked at conditions on that P sub j of t. So the conditions on the conditions on the lambdas, we kind of have to also look at it from the conditions of P sub j of t, which is just thinking of the probability of removing a bug to be a function of time. Okay. That's all I have, and just some papers. Some of it I mentioned in the talk. Some are like the results that I mentioned in the second part. So I think this one with half, Atul Huff, that's the one that he looked at the finite sample properties of the Littlewood model. And the one with Nick Thompson, he was the one who kind of looked at the model one. I believe he looked at also I think adding a bug, I think, for this one. And those are the other papers. And again, thank you for having me. And that's all I have for you. And remember, for the simulation part, so again, I'm showing my age here. When I first did the simulation, we did it in Fortran. Fortran. But our students now, they did their simulation. I think they use it in R. I think they could have also done it in C, but or MATLAB. I think I have one student, he did his simulation in MATLAB. because he was more of like applied math person, who used MATLAB. But Jackson Huff and Nick Thompson, they did it in R. R, good thing with R, it's free. Software instead.
This into
Excel.
MRSS.
But some courses are, what's the step?
Yeah, actually, even I remember, even our biology faculty, we offer a stat for the sciences. They actually said, "Can you teach it with R?" Because we used to use Minitab, we just like Excel. Minitab, if you have also taught SPSS, for the social sciences. Minitab is used for more engineering, but the biology faculty, we were surprised. They said, "Well, can you teach it with R?" So we have to kind of modify some of our computer lab, to use R. And R has a lot of capabilities with doing simulation. So it's open access.
Used to be SAS. That was expensive.
And the good thing with those open access, if you actually like say you have a new procedure that you have, they put it in the library. I mean that's the whole idea. You build up that library. So people who would be using it, you don't have to recreate the wheel, so to speak.
So, some of the students can get in touch with you.
Yes,
Be happy to.
we'll be happy to collaborate.
So, and in the recorded instrument. So the sound of class. So it's so far. We don't know about possibly six semesters. Yeah. There's a lot of the variants and applying
Because failed to mention, but when you're estimating those parameters, the function that you're becomes so flat. So it becomes so flat that obviously if you pick an initial value, that can bring you out there. So we kind of have, at least when I started, you know what, let's use even even if it's slow, but then something that could give you a good guess. So I think what I did initially was that kind of just use some sort of like a bisection method. Because bisection is slow, but you typically could get a good solution. And then once you get a good solution, then that solution now you could do some Newton-Raphson method, and then you'll be able to get a good one. So, but that was the difficulty because it looked so flat. There was also a condition that we found. I think that mock paper basically also gave us a condition wherein if let's say at some point you don't satisfy this certain inequality, you're not gonna get solution. So in a way, it was good because you kind of have there's a way to check. So when you check it and then it satisfies that you know you will be able to find one. Still, because of the flatness of the function you're maximizing, uh, it provided some difficulty. So I think even for some of our undergrads, they have to do their senior projects, what we call like a mini thesis for undergrads. So those are some good problems that they could work on because at least you know that there's a solution to it. It's not you're asking them to really find something new. So
for now. So they're not allowed joining entry or
Thank you.
it's where taking the chance to visit
Oh, it's a pleasure. It's our pleasure.
again. We're having the station.
Thank you.
They're not there. She should have. Also,
We're holding G. Early days. G. Speakers. Students.
It's a calculated space or on a college job.
For example. This does not. So we will ask the questions about. So. So more complication.